Hi, and welcome to Module 2 of Lecture 14. In the previous module, we discussed the gradient. The gradient, if you recall, was the vector composed of the partial derivatives of each of the function with respect to each of the variables of which the function is a function. That gives you in some sense, that tells you things like what is the rate of change of the function along each of the dimensions, holding all other variables constant. And as a whole, the gradient tells you the direction of greatest change of the function. And that's all fine as long as the individual variables are in some senses fundamental, right? There's no smaller piece that we care about. x1, x2, and x3 are the smallest pieces we care about, and we're interested in knowing how f, the function, changes with each one of those variables. What if, though, you miss something? Consider a case of spurious causation, right, in which you think A causes B, but in reality there's some other variable that causes both A and B, right, some third thing. Well, in order to make use of that messes up your causation, right? If your story is A causes B, and it's really some third thing that causes both of them, you're not really getting at the proper causation of the proper causal story, right? You're not getting at the proper causal story. You're saying A causes B when really C causes A and B. How do you incorporate that in terms of underlying math, right? The math doesn't know you messed up, I guess. The math is just math. So how do you incorporate the information? Well, you can say that you originally wrote this, say f equals some function of, let's say, you originally thought this was true, right? This is your original guess. But it turns out there's some variable t. And it turns out t is actually causing x1 and x2 and f. So what do you do about that? Well, unlike your sort of causal story verbally, where you have to go through and just say you're wrong, right? There's other variables causing both those things, and you had spurious causation. Here instead, what you can do is just make x itself a function of t, and x2 will also be a function of t. Now, nothing's wrong anymore, right? It seems like x1 and x2 are causing f, and they might be, but at a deeper level, t is causing x1 and x2, and then indirectly causing f. So how do you do this? Well, the way you can do this first is by assigning some function of t. Let's say this is 3t squared, and this is t minus 2. Okay. Now, how do we deal with this, right? How would you understand the true thing you care about, which is not how f changes with x1 or x2, but rather how f changes with t, the underlying real causal variable here, right? Not the intermediary variables x1 and x2, but the actual thing that's causing both things. T. How do you figure this out? Well, this we call a total derivative. Note that the notation for a total derivative is exactly the same as the notation we used before for a derivative in one dimension. And the reason is they're the same thing. Right? They're exactly the same thing. We were implicitly doing a total derivative in the case of one variable because we only had one variable, and therefore it automatically was a total derivative. Here now we have more than one variable, so how do we deal with that? Well, it turns out we can use basically an analog to the chain rule in more than one dimension to figure this out in a pretty straightforward fashion. Well, if we go through and consider each one of these things, you get the total derivative, which has all of the relevant variables here, right? So what it says is, let's go term by term here. The first term is the change in the direct change in f with respect to t. The second and third terms capture the indirect change in f with respect to t as mediated by x1 or x2. Right, so this first term here is the change in f that is due to t changing x1, which then changed f. And the second term here, third term overall, tells you the rate of change in f with respect to t as mediated by x2. So t changes x2, then x2 changes f. So a change in t induces a change in x2, then that change in x2 induces a change in f. So t is causing the change in f, but x2 is intermediary in a sense. In each case, you have to include the partial of f with respect to the relevant variable, which tells you how the f is directly changing with respect to that variable, holding everything else constant. And then the second term in each product here tells you the total derivative of how that particular variable is changing with the underlying variable of interest t. Now the first one over here, the rate at which t changes with t is 1. So often you see this one just removed completely because it's just 1. And this first term here you refer to as the direct effect of t. In our example, there is no direct effect of t. But if I were to add, t squared, then the direct effect of t would be due to this term right here only. Now these two are the indirect effects of t. So we refer to these as the indirect effects of t because they capture how t affects f via x1 or x2. I can go through and actually solve this thing, and I did not make myself much room, but we can try it. So what's partial f partial t? Well, there's only one t now. There's a t squared. So the first term is going to equal 2t. Now that's not the only way t affects f. T affects f directly, but also indirectly through x1 and x2. So what's the partial of f with respect to x1? Well, I'm going to have to skip steps here because there's not any room, so make sure you do it at home. 2x1 plus 2x2 is partial f partial x1 times dx1 dt. What's dx1 dt? Well, right over here is our function there. So what's the derivative of that with respect to t? Well, 3 is a constant, so it's the derivative of t squared, which is 2t. So that's a total of 6t. Now we go back over here. What's the partial f partial x2? Well, here x2 appears only one place. You treat x1 as a constant, so this is just 2x1. And then what's dx2 dt? Well, over here, and red, yep, you get t minus 2. The derivative of t minus 2 is just 1, so this would just be 1. And that's it. Now this isn't quite finished because we still have x1s next 2 in there. We don't want the x1s next 2. So what we can do is plug back in at the very end. 2x1 is 6t squared. 2x2 is 2t minus 2 times 6t. And 2x1 again is 6t squared times 1. And you can go through, if you had more room, we can go through and simplify this and put all the t's together. But the upshot is, that's it. Now, you could also have done this by plugging into the very beginning equation over here, x1 and x2, and then you would have taken the derivative of the t and it worked just fine. You can always do that, it'll always work. It's just that in general, you might have a much more complicated scenario than this, and it won't be as easy to do that as it is to apply the definition of the total derivative. So there's your example, and there's what it is. It could be a little more general here for the total derivative. So there's the first term, the direct effect. And if you had more than one variable, say n variables, you would have df dxi times dxi dt. And that's the general equation for the total derivative. It tells you how the function is changing with some parameter t, where you have all these intermediate xi's that are mediating the effect of t on f. So there you go. And I should say this, so spurious causation is not the only way you see this. There's two other ways you see this. We saw this also when we calculated integrals. When we try to change variables from, say, x to u, what we did, we sort of hand wave through until we can multiply both sides by effectively du dx, dx du. Well, if you take the equation for the total derivative and you effectively multiply by the dt, you get what's known as a total differential. The total differential looks like this. What this is effectively is a change in variables formula. If you got rid of all the sums there and had a single xi, right, and you call it, and what you're effectively doing there is changing from x to u or from u to x, and it's the exact same formula we ended up using when we had to take integrals. So using total differentials is connected to how one computes integrals when one changes variables. So you've seen that particular use before. A second use is in comparative statics, right? We discussed comparative statics a little bit before in these lectures. That's 2 lectures. Comparative statics tell you how an equilibrium of some game changes with respect to the parameters of the game. Here you can think of the parameters as t, and we're trying to understand how some larger thing changes with parameters. However, the parameters don't act directly necessarily, they act indirectly through their effect on, say, strategies that individuals choose. So we have to use a total derivative to compute how the change in parameters affects some larger change as mediated by actions within the game itself. That's it. So I covered the total derivative here. In the next module, we're going to deal with cases in which the function is vector valued. Thank you very much.